All right, so now we're ready to talk about electricity. Electricity and magnetism. This is a really fun chapter. I really hope you guys all enjoy this chapter. But before we start, let's talk about the history of electricity. This actually has a really fun story to begin with. The ancient Greeks discovered a very interesting property of amber. Now, if you know what amber is, it's basically just dried tree sap. That's pretty much all that amber is. I have a plastic here that actually has properties very similar to amber. Here's what they saw. If you take amber and rub it against a piece of fur like so, and then suspend this amber, as I am doing so right now. Perfect. And then you have another stick, say piece of glass, and rub it against a piece of fabric, then they're going to actually start exhibiting attractive properties. As I finish rubbing that, I'll bring the glass close, and what we see is that I start causing the amber to spin. And I can stop it and cause it to spin the other way. And I can just keep doing that over and over again. It's a very attractive force, and I can get it spinning very, very fast. Now, here's the interesting thing. If you learn any ancient Greek, what you learn is that the word for amber was electron. That's where the term electron comes from. So for many years after that, this property, this electron attraction or amber effect, was quite a mystery. Well, over the last 150 years, we have learned so much about this. There's still some of it that's mysterious, but most of it we understand a lot better now. In fact, we have another name for this amber effect. This amber effect we call now as static electricity. And we know it is the attraction between two differently charged objects. It's the first American physicist, the first famous American physicist, who coined a notation for these two opposite charges. That scientist was Benjamin Franklin, and he coined positive and negative charges. And he said that if we look at these two, we'll take the amber and call that negative, and the glass will call that positive. And so glass, being negative, stuck with the name amber, or its Greek root, electron. That's why electrons are denoted as having a negative charge. Now, fast forward from the time of Benjamin Franklin, we have learned that the negative charge in the amber is due to a part of the atom that we call today the electron, and the positive charge in the glass rods is due to the part of the atom that we call a proton. Now, the electrons and the protons will attract each other, whereas if you take an electron and bring it close to another electron, they will actually repel each other. Now, we have gone so far beyond just knowing that positive and negative charges attract, negative charges repel each other. And that knowledge that we've gained beyond that has become the basis of our modern use of electricity. When you look at an atom, there are two main parts to the atom. One is the nucleus, the very center of the atom, which is made of subatomic particles named protons and neutrons. Protons are positively charged, using Ben Franklin's notation, and neutrons are neutrally charged. They have no charge at all. The other part of the atom is this cloud region, this pink cloud indicated here in this figure. We call this an electron cloud. It is a region where electrons, or negatively charged particle, orbit around the nucleus. Now, in a typical atom, you have a certain number of protons, or positively charged particles, and the same number of electrons orbiting the nucleus. And as a result, you'll have positive 2 charges from the nucleus, negative 2 charges from the electrons, giving you a total net charge of 0. This is what we call a neutrally charged atom. Now, here's a good example of how we can get a misbalance of charge. First of all, let's look before it changes. You have hair and a comb. Inside of the hair, you have positive and negative charges, but they are perfectly balanced. You have a net charge of 0. Inside of a comb, you have the same. You have a net charge of 0. But the net charge won't always be 0. Every once in a while, you might lose an electron. And if you lose an electron, then that gives you one more proton than you have electrons, which gives you a net positive charge of positive 1. Another thing that could happen is you could actually gain a third electron. So you end up having one more electron than you have protons, giving you a net negative charge. Now, using our hair and comb example, if you brush a comb through the hair, you might strip some of the electrons from the hair, and the electrons will attach themselves to the comb, which means that here in the hair, you have lost 2 electrons, giving you a net charge of positive 2. And then in the comb, you have 2 more extra electrons, giving you a net charge of negative 2. Now, great example of doing this would be, say, when you have a balloon. You rub it in your hair, you're doing the exact same thing. You're stripping some electrons from your hair, they're going into the balloon. You pull up the balloon, your hair will stand up on end, and it'll be attracted to the balloon. That's basically the positive charge of the hair being attracted to the negative charge of the balloon. When we talk about measuring electric charge, we measure charge in units of coulombs. Now, Coulomb was a scientist who did some phenomenal work in electricity and developed an equation that tells us the magnitude of electric forces. So we use coulombs as the unit for electric charge. Now, since charge is caused by nothing more than either extra electrons or missing electrons, then the total charge has to be a multiple of the number of electrons missing, or the number of extra electrons. So, bottom line, any quantity of charge has to be a multiple of the charge of one single electron. So the total charge is going to be the number of electrons that are either missing or that are extra times the charge of one single electron. We indicate that as Q, the total charge, equals N, the number of electrons, times E, the charge of one electron. And the charge of one single electron has the value of 1.6 times 10 to the minus 19th coulombs. So how many electrons are in a charge of 1 coulomb? Well, we just barely saw that the total charge is going to equal the number of electrons times the charge of an electron. So what we're after is N, how many electrons there are. So let's say if we want to solve for N, it's just going to be Q divided by E. Well, the charge we're dealing with is 1 coulomb. We divide that by the charge of 1 electron, which we saw was 1.6 times 10 to the minus 19th coulombs. If you take a second, plug that into a calculator, what you'll find is that this comes out to 6.25 times 10 to the 18th electrons. that would be 6 1/4 quintillion electrons. So you can see that that is a lot of electrons, quite a bit. Another example, let's ask what is the total charge of, say, 5 billion electrons. Again, we have our total charge is going to equal number of electrons times the charge of one electron. We want to know the total charge, so that's Q. So Q is going to equal the number of electrons, 5 billion, times the charge of one electron, 1.6 times 10 to the minus 19th coulombs. This is a total charge of 8.0 times 10 to the minus 10th coulombs, which would be about 0.8 nanocoulombs. It's really tiny. So not a lot, even though there are 5 billion electrons, the charge is still in the nanocoulomb region.